Welcome to the HPC Best Practices webinar series. The series is brought to you by the IDEAS Productivity Project, which is part of the exascale computing project of the US Department of Energy. The series is a collaboration involving the computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marquez from Berkeley and Ashley Barker from Oak Ridge, and I'll be the hostess for today's webinar, Migrating to Heterogeneous Computing, Lessons Learned in the Sierra and the Capitan Centers of Excellence. And the webinar will be presented by David Richards. David is a computational physicist in the Center for Applied Scientific Computing at Lawrence Livermore. He received a bachelor's in physics from Harvey Mudd College and a PhD in physics from the University of Illinois at Urbana-Champaign. He joined Lawrence Livermore in 2006 and has over 20 years of experience in scientific computing as both a user and application developer in academic, industrial, and national lab settings. Currently, David leads the Capitan Center of Excellence and Advanced Architecture and Portability Specialist team at Livermore. He's also the PI for the ECP Proxy App project. This is the 50th webinar in the HPC Best Practices series in the ECP project. And we'd like to thank all the 80,000 plus people who have signed up for all these webinars in the series. We have issued more than 200 tickets for today's webinar, and all attendees have been muted upon entry. We'll be receiving questions through the Zoom chat and also the Google Doc. I pasted that address in the chat already. And the webinar will have breaks so the speaker can respond to the questions that, that come in. With that, David, I'll stop my sharing.
All right, I think that's what you want to see, yes?
Yes, David.
Very good. All right, so first of all, thanks to Osni and Ashley for inviting me to give this talk. Good morning or good afternoon, I guess, depending on what time zone you're in. And Osni, feel free, if I've not got enough screen real estate here to monitor chat. So if you see any good questions, feel free to chime in and ask those.
I will.
So I'm going to talk about some of the lessons that we have learned migrating to heterogeneous architectures in the process of preparing for the Sierra supercomputer, which is, of course, now in production at Lawrence Livermore, and our next computer, El Capitan, which will be delivered in 2023. This talk began life, I suppose, as a paper that we wrote back in 2019 that was published in a special issue of the IBM Journal of Research and Development, where we tried to assemble some of the lessons that we learned for the in the Sierra COE. I do want to thank the many people who contributed to that paper and to that work. Code teams, support staff, vendors, anyone who contributed to the success of Sierra, and also people who are working with us now on El Capitan. I've tried to list some of them, but I'm sure I've missed some. Again, this talk, it began quite a while ago, and some of the slides you're going to see here are probably a little old, but the lessons I think are still very relevant, and so I hope you'll find some benefit here. Let's see. So for those of you who may be unfamiliar with the idea of a center of excellence, it's a close partnership between the NNSA, between national labs, and the vendors who are providing our systems. The core concept here is that the vendor staff and the lab staff can work together to establish joint work plans. We can share information, and the COE provides a powerful collaboration mechanism. The vendor staff get to work alongside the code teams. Some of the vendor employees are even assigned, at least in non-COVID times, to work right on the lab site. And we are able to provide access to our codes, including even classified codes for those who have security clearances. And in return, the vendors are able to provide non-public information about their hardware and software, and even give us early access to hardware and software. This idea of combining the vendors and the lab staff in this collaborative relationship has really become a recognized best practice for our large DOE system procurements. And I think you'll find that essentially almost any large system that's being purchased by the DOE has some kind of center of excellence arrangement. So that's where that term comes from, and that's what we mean when we talk about center of excellence. All right, I also want to call attention to the fact that we're clearly in the heterogeneous era now. If you look at the current, big four procurements that are either quite recent in the case of Perlmutter or upcoming have been announced, that the Office of Science and the NSA have announced. We've got Perlmutter, Frontier, Aurora, El Capitan. All of these are going to be GPU-based machines. And they're going to be GPU-based machines with GPUs from 3 different companies. So, performance portability is going to be an issue. And, if you want to run on the leadership, the flagship systems, you're going to have to be prepared to work in these heterogeneous architectures. Another thing I'll point out about the situation is if you look at these machines that are being delivered now through 2023, these machines are going to run for 5-7 years. We're going to be operating these machines well into the end of the 2020s. And so the investments that we're making now to run these machines those are investments that we're going to have to live with for a number of years. So it's important that we be comfortable with what we're doing. It's important that it be sustainable. And it's, again, also important that you realize this is not a flash in the pan. These are the big machines that we're going to have for quite a while. In kind of finishing up some of my introductory comments, I guess I want to kind of put the lead up front, and that is that our switch to GPU-based computing is really paying off with some really huge performance increases on Sierra. And I'm showing a few of the flagship codes that we run on Sierra, and some of the kinds of speed ups that we're seeing. These are speed ups comparing one node on Sierra relative to a dual socket Broadwell node. Now, I know that speed up is a flawed metric, but coming up with a better one is challenging at best. And certainly one thing that these kinds of speed ups, or at least looking at these speed up numbers, does allow you to evaluate is the kind of improvements in user productivity that we're seeing on GPUs. When you look at being able to speed up a code by something like a factor of 10, you're talking about taking a simulation that used to take a day and now being able to finish it before lunch. So that gives you an opportunity to iterate many times a day, or at least several times a day, rather than once a day. It gives you an opportunity to do in a day something that used to take a week. And we're finding at Livermore that that's making a big difference to the way we're able to conduct science, and we're able to ask and answer questions. So these speedups are actually very significant and have made a big difference to our ability to complete our mission here at the lab. And I'll say a little bit more about measuring performance and ways to evaluate performance later in the talk. All right. One other, I guess, set of comments by way of introduction. I want to talk a little bit about the nature of our codes at Livermore. For the Sierra COE, we were really concerned with large integrated multiphysics codes that are tailored to our mission space and target a broad range of application domains. As a rule, these codes have outlived the systems that they were originally designed for, and most are expected to outlive Sierra. In fact, we're preparing these codes now to run on El Capitan. The codes are large, millions of lines of code, numerous library dependencies. The developer teams are large, and they are composed of staff with various levels of CS expertise. It's also important to point out that these codes are used in production on a daily basis, so they need to continue to operate reliably even as we go through the process of refactoring them and adapting them for new architectures. Finally, these codes need to be portable not only across time from one architecture to another as we bring on new machines, but they also need to be portable today across a wide variety of current systems, all the way from laptops and workstations, all the way to our largest supercomputers. So migrating these codes to new architectures is a significant challenge, and this is where we've learned our lessons in the COE. That's probably a good spot for me to pause and see if there are any questions so far.
Not yet, David.
Okay, good. Let's carry on. So the first lesson that I want to share today is that successful migration tends to follow a consistent pattern. Now, teams aren't necessarily going to use all the steps that you see here or perform them in exactly the order that I've given, but we think this is a pretty good template. One of the first things that you're going to have to do in moving to GPU architectures is getting rid of GPU anti-patterns, such as global variables and certain standard template library constructs that simply won't work in the highly threaded environment of a GPU. In fact, you probably may not even be able to build your code for a GPU until the refactoring is complete. Now, if you look at the graphic on the right, this is showing the major events in the timeline of one code migration effort that we reconstructed looking through their source code repository. And right there in the middle, you can see where the global variable removal was completed. You can also see that this effort actually took quite a while. Again, part of that was due to the fact that this team had to support production applications as they were going. It's also the fact that this was one of our earliest attempts to go through this migration pattern, and so we were learning as we go. I think it's likely that a smaller code could go faster, and even a larger code could go faster based on the lessons that we've learned today. Step 2 is to create a mini app and explore design space. Now, it may seem counterintuitive to spend precious developer time working outside your main code, but we find over and over that the time spent making a mini app pays for itself. And I'll say more about mini apps and proxy apps in the next few slides. In step 3, it's pretty clear that portable abstractions and frameworks like Raja and Cocos are the best choice for code that performs well across platforms. And I'll say more about Raja in a minute. Number 4, we've learned that it's best to focus on a specific use case and strictly limit porting efforts to the code that is absolutely necessary to support that use case. Now, there are 2 reasons for this advice. First of all, porting a large application all at once can really seem like an overwhelming job. It can, suppress morale and just make things seem really hard. Focusing on a specific capability keeps the amount of code that you need to deal with tractable and gives you an achievable goal. Second, in the course of porting one use case, you're likely to learn quite a bit about the overall migration strategy for your code. That will help reduce mistakes and make it easier to extend your porting into additional use cases. Now, you can see the strategy in action on the right with the different blue and green milestones. They start with a single major physics package and then add more capability as time progresses. 5th, search for additional parallelism. To get good GPU performance, you're going to need, or at least you may need, new algorithms or new numerical methods. For example, at Livermore, we had a large effort focused on, we have currently a large effort focused on higher order methods since they have better mathematical intensity. Obviously, that search is going to be highly application specific. Step 6, manually manage memory and data motion between host and device. Unified and coherent memory on modern systems may allow you to get your code running without worrying about explicit data transfers. And that's a great first step, but likely your code won't perform very well. And most teams find that some of the easiest low-hanging fruit for optimization is managing their data transfers. Finally, step 7 is to do it all again, because optimization is almost always an iterative process. Now, again, I pointed out this is a multi-year process for this code, but we've learned a lot since this started, and the supporting ecosystem is a lot better than it was back in 2015. So you still won't be able to port a significant code in a few weeks, but again, the time will likely be reduced to what is shown here. All right, so to go into some more detail about a few of these steps, I want to drill a little bit deeper, and let's start with proxy apps.
Hey, David, there were a couple of questions, if I may.
Sure, go ahead.
What portable abstractions are recommended for Fortran codes?
We're going to say a little bit more about that later. The short version is OpenMP, and I've got a slide coming on that in about 4 or 5 slides, so we'll say more then.
Okay, maybe then the other question we can address later as well. Okay,
great, thanks. All right, so I'm showing here some results from a couple of proxy apps that we've used in the Sierra and El Capitan Centers of Excellence. On the left here, you see some results that we got out of Quicksilver, which is a proxy app for a Monte Carlo transport called Mercury. When Mercury was first adapted for threaded CPUs, we used a strategy where every thread got its own private copy of every data structure that a thread could write to. We called that the fat thread strategy because, well, it used a lot of memory, and the threads each had a large amount of memory assigned to them. That prevented data races, but again, used a fair amount of memory. As we considered our GPU ports, we realized that it was going to be impossible to have that much data replication and have a separate copy of the memory for every GPU thread. We wanted to try out the idea of using atomics to manage the data races. That we called the thin thread strategy, because again, the threads would not have to have their own private memory. And it turned out that it was much easier to prototype that strategy in a proxy app than it was to try and get the entire application working. And you can see that we found that with the exception of a buggy compiler on the Pascal GPU, the thin thread strategy performed really just about as well as the fat thread strategy, and that gave us the confidence we needed to move forward in the main application. On the right, I'm showing some results of a proxy app called Comb, which represents the data packing and communication for the Halo exchange in Aries. One of the things we learned from looking at this Halo exchange in Aries is that especially as the size of the problem decreases, the amount of time that you spend in the Halo exchange is dominated not by the time communicating the data, which is shown in the blue, but it's actually dominated by the time that you spend packing data into the communication buffers. And heterogeneous architectures have complicated that packing step. Because your data is likely to be on the GPU, if you need to pack the data into the buffer that you're going to hand to MPI, that's often a non-stride one kind of packing, you have two choices. You can call a GPU kernel. Unfortunately, for small packing operations, the launch overhead can exceed the runtime of the kernel, or you can move the data back to the CPU, which has its own performance overheads. So having this proxy app has really allowed us to drill into this, to focus on what are the best techniques depending on architecture, depending on compilers, depending on problem size. And it's also enabled us to really expose this issue to vendors, explore design options, and proxy apps in general have just proven very useful for benchmarking and co-design interactions for vendors. So over time, the time that we've spent working on these proxy apps has really paid for itself. All right. I talked about portability abstractions, and Raja has been very successful for us at Lawrence Livermore. Cocos, of course, is another very popular portability abstraction, and they have many, many things in common. I'm going to speak about Raja, but nearly everything I'm going to say also applies to Cocos. And I want to highlight two aspects of Raja that I think are very important to success and that you should be looking for as you look for a portability layer in your code. The first thing I want to highlight is that Raja provides specific abstractions to control and reason about parallel workloads. And I've highlighted those three things over here on the left side of the slide. First of all, you get to specify in Raja exactly the parallel pattern that you're trying to use. It can be a parallel for all, a reduction, a scan, etc. Second, you get to specify an execution policy, which is how the loop runs or on what hardware the loop runs, whether it runs on a GPU, on a CPU, etc. Finally, you get to specify an index set, which is the range over which that parallel pattern is to operate. And depending on the execution policy, it may even allow you to specify the order and optimize that order according to the hardware. The second thing I want to point out about Raja is that when you use Raja, when you use these parallel abstractions, you're no longer writing sequential loops. You're writing inherently parallel code. If you look at the example on the right, even though those loop bodies look the same, in the C-style loop, you're writing sequential serialized code that can only become parallel if a compiler somehow figures out how to parallelize it. On the other hand, in the Raja style loop, you're actually writing a kernel. And kernels have distinct advantages for compilation and for optimization over these parallel loops. Now, Tom Skoglund actually gave a great talk on this back in the P3HPC forum back in 2020, and there's a link to that talk in the references at the end of the slide. So if you want to understand better why writing kernels is better than writing loops, I highly encourage you to take a look at that talk. All right. The next thing I want to talk about is coherent unified memory. It's helpful, but it's not a panacea. And in fact, really multiple paths to success have emerged as we look across the codes here at the lab. I'll highlight 3 of them in particular. So first of all, SW4. SW4 is a seismic wave code. They use managed memory to handle their data transfers. Because of the nature of their code, once the managed memory system moves the data to the GPU, they tend to stay on the GPU for a long time. They've also used some hints which tell the unified memory system to leave the data on the GPU even if it's accessed on the CPU and do zero copy. Because so much of their code is on the GPU, and because the CPU operations they need to do are either so infrequent or have to transfer such a minor amount of memory, the lack of performance or the performance penalty they pay by having the system move the data is sufficiently small that it doesn't impact them. They essentially amortize that overhead by the reuse between the transfers. So they find that the ease of just letting the system handle it far outweighs any very tiny performance impacts that they have. Aries, on the other hand, has had to make nearly all their data transfers explicit to get the performance they're looking for. They do find that managed memory pointers are helpful for libraries and for code simplicity. So there are still some managed memory pointers hanging around, but most of their data transfers have had to be explicit for performance. And then in Teton, which is actually a Fortran code, all of their data transfers are explicit. I'll point out that there are some abstractions that you can use to improve code performance and developer productivity. We have a smart pointer abstraction that automates explicit data transfers. That's heavily used by Ardra and AL3D. That's called Chai. And I'm going to say a little bit more on the next slide about Umpire, which is our portable API for third-party memory capabilities that helps coordinate memory use and introspection among packages. However you handle unified memory, host data transfers have to be treated as first-class concerns if you want to get good performance. I see the chat number going up. Osni, is there a question here?
Yeah, but I think we can
okay,
wait a little bit. Yes.
All right. So a little bit more about Umpire. Umpire is a library that we're developing. It's an open source library that you can find out on GitHub that we are using to coordinate complex memory allocations and movement in complex applications. So I'm showing here an example of one of the things that we're using Umpire for. Assume that you have a complex code which is using multiple libraries, say A, B, and C, each of which has their own view of GPU memory resources. They might all start by staging their data on the CPU. A executes first, needs a temporary memory pool. A can copy some of its data to the GPU. In phase 2, some of that data will be copied back, but that temporary pool can stay allocated on the GPU, and Umpire provides a mechanism for those libraries to share that temporary pool. So B and C can use that same temporary pool, thus preserving resources on the GPU and just overall coordinating that scarce resource. So we found that Umpire is a very useful library to have. It has not only these abilities to coordinate the resources, but it's got a lot of memory tracking capabilities. And it, again, also provides portability across the different memory APIs that different vendors are providing. So I highly recommend that you look into Umpire as a way of managing your memory on GPUs. All right. To sort of begin to wrap up this section on application migration, I want to show kind of what this iterative performance improvement really looks like in practice using the Lagrange hydro capability in Aries as an example. As you can see from the graph on the left, the first time the Aries team ran the code on the GPU, it was 100 times slower than the corresponding CPU code. That's the kind of result that makes you really question your life choices and makes you think about giving up. But I have to compliment the Aries team on their determination. Through a series of optimizations, code transformations, they gradually improved the performance of their code until it became more than 5x faster than the corresponding CPU code. And as you can see, this is a pretty old graph, since it stops really at early availability access for Sierra. So this actually stopped even before we had Sierra. If you go on today, that code is even better today. And so the takeaway message here is that repetitive processes aren't just for hair care. You really do have to optimize, you really do have to iterate, and it can be a long process. Sustained effort, long time, many people, and the vendor partners and the COE were really critical for achieving this success. All right, here is the promised slide on Fortran. Now, Lawrence Livermore, we are very heavily invested in C and C++ and Raja, but I know it's not the case everywhere. And I know there are still a lot of Fortran codes around. One of the big issues that we face is that the C and the C++ standards and even the OpenMP standard are really advancing rapidly, and they're becoming more and more complicated, and there are more and more complicated features that have to be implemented in those compilers. All of those changes are straining vendor resources, so it really shouldn't be that big of a surprise that Fortran support is, well, probably lagging compared to C or C++. The only reasonable choice that we have found for GPU coding and Fortran with any kind of portability is OpenMP. Unfortunately, it's just not as well supported. Now, the FLANG, the F18 project is likely to help. Those projects are making good progress, but they're still making progress, and they're not going to be ready for a little while yet. Unfortunately, Fortran just doesn't provide a mechanism for the kinds of abstraction layers that Cocos and Raja provide. The thing I will tell you about Fortran is that if you want your Fortran porting efforts to go easily, try to write your Fortran so it looks as much like C code as possible. And unfortunately, I have to tell you that also avoiding modern Fortran features is also a good way to make your life easier when it comes to getting on the GPUs. As we look at our codes and look at where the pain points are in getting them to function, getting our Fortran OMP offload to work, the modern Fortran features tend to be the most problematic, especially shaped arrays and array notation. The best advice I can give is that up-to-date proxies and up-to-date tests are really, really critical for ensuring that compilers will function as desired. And because the Fortran community, even though it may be large in our particular scientific community, the Fortran community is still relatively small compared to C++. And so pooling our efforts and spreading the overhead and the effort is probably the best thing we can do to help the compilers and help the vendors provide the best Fortran support that we can. Questions we should take now, Osmi?
Yeah, there is a related question here. OpenACC Fortran is a successful option as well. Why isn't it mentioned here?
So OpenACC is not going to be supported on future compilers. That's unfortunately just a fact, at least as far as my visibility is showing us. I realize it's been successful. We have no plans to support OpenACC on El Capitan. I'm not aware of any plans to, it's not going to be a community supported standard anymore. And I'm sorry to say that, but that just seems to be the situation as I see it.
Okay, so I think there are other questions here. If you think it's appropriate, this going back some slides, David.
Sure, let's go ahead.
Okay, so what about switching to APIs which utilize the various compute units? For example, Chapel, Intel One API, OpenCL, for a single code base?
So look, every code base is going to have to make their own decisions. And it really depends on the size of your code base and how much time you have to optimize particular pieces of code. I can think of a particular code that we work with where the developer has said, look, our performance critical sections are limited to a relatively small amount of code that our code team can afford to rewrite in a highly vendor specific, highly tuned manner every time a new architecture comes along. And if that describes your code well, then you can feel free to choose whatever works best on that piece of hardware. On the other hand, we've got large codes that, you know, some of these codes started before their current developers were even born. Those are codes where they don't have that kind of flexibility to rewrite, you know, even performance critical parts of the code. There aren't, you know, one or two or a small number of hot loops. And so in those cases, finding something which is, you know, truly vendor agnostic and truly portable is the highest priority. That's why we have focused on Cocos and Raja, because we can get those abstractions to compile down to whatever vendor specific API is available for the hardware. Does that answer the question?
I hope so. Let's see. Yes, yes, yes.
Oh, good. Ah, thanks.
And,
all right.
And since we are there, David, is it possible to use Raja to target both the CPU and GPU simultaneously? If yes,
so
how?
The answer is yes. That is an active area of work. There's a project whose name I forget at the moment that is even looking at trying to figure out how you can basically collect data on the fly as you run to determine where to put various Raja kernels and how to divide those Raja kernels between the CPU and GPU as you go. So yes, that is possible, but I would encourage you to get in touch with Raja developers if you're interested in those kinds of features, because I'm sure they can tell you more.
Another one here, what about using DMA-like operations from the GPU to avoid copying data back to the CPU or system MMU to have GPU and CPU units access the same memory to avoid performance degradation?
So that is, there are some possibilities to do that if you're talking about network operations. And we've had some success with that sort of thing. But when you're talking about, again, compute-oriented, we have not yet found a way to do, for example, the pack operation that you need to do for a communication operation through a DMA engine. Although that is one thing I suggested to vendors is there was a way that we could program the DMA engines so they could do some of those kinds of gather or scatter operations. That might be a way to avoid some of the kinds of bottlenecks you mentioned.
All right, David, let me see here. Okay, performance supportability is a hot topic, but reproducibility is not often mentioned, but it's of course important as well. How does reproducibility fit in? Is it possible to some extent precision?
So you know, we could probably spend an entire talk just on reproducibility, and it's a tough issue. One thing I will say, and again, I know I'm flogging Raja and Cocos, but they have a lot of advantages. One of the advantages that you have with Raja and Cocos is you can take the code that you've written in Raja and Cocos and you can say, I want to run this code in a sequential CPU context. That at least, that tends to eliminate many, if not all, of the reproducibility kinds of issues that you see in parallel code. That can help you give confidence that your code is functioning well. Or if you're seeing problems, get back into that sequential context and find a way to debug it. You can then step up to a threaded kind of run on a CPU, which has better debugging tools, better data race tools, other kinds of tools that can help you find problems that might be contributing to reproducibility that are actual problems as compared to just the inherent differences in results that you get because of parallelization. And because you're running the same code, just changing the parallelization strategy, changing the hardware you're running on, that can help you manage some of the reproducibility issues and help you find real bugs that and distinguish between what is just a difference in results due to parallelization versus a real error.
So David, going back to the Fortran, could you say a little more about, say, Raja plus Fortran or Cocos plus Fortran?
So, I mean, we certainly have ways of taking Raja and Cocos code and calling it from Fortran, but I'm not aware of any mechanism that has been successfully demonstrated that can apply that kind of abstraction, you know, a Raja-like or a Fortran-like abstraction directly to Fortran code.
Okay, so to the participants, I'm going to make sure that David goes through the questions afterwards, and we sanitize the answers. Okay, all questions will be answered later. Please continue, David.
All right. So want to finish up this section with just a couple of other things that we're learning in the El Capitan Center of Excellence. Recently in the El Capitan COE, we started using a 3-stage readiness process to prepare both our applications and the system software environment. Especially for El Capitan, we are finding that it's just as important to make sure that the system software like compilers and debuggers and performance tools are ready to run. It's just as important to get those tools ready as it is our applications themselves. And so we've kind of, as I said, put together this 3-level or 3-stage process that begins with basic build and run testing, getting rid of the show-stopping problems in the application or the software stack, just trying to find big problems as soon as possible. Now, you might still need to have some workarounds to get your code running, but just getting that first build and run on, I've got a typo there, it should be CPU and GPU, and get basic operations of the debuggers and the performance tools. Once you have those basic operations going, the next level is to begin using the performance analysis tools, using the debugging tools, comprehensive tool tests to establish performance baselines and figure out where the application bottlenecks are. This shows that those performance tools are actually ready and capable of doing the kind of analysis that developers need, and helps find issues in those tools that we're going to want to solve for the future. Finally, level 3 is where we begin to optimize code performance and test tools at scale. We've already talked about the fact that optimization is almost always iterative. And so level 3 kind of spins until the code team is satisfied with their results. Taking it through this staged approach has proved useful for us to find problems with the tools and also find workarounds for problems in the codes and make progress as the tools improve, as the compilers improve, and as the applications get ready for El Capitan. And it's also important with El Capitan because unlike Sierra, where we had a lot of Raja conversion to do, a lot of our codes are already in Raja, and so there is less work that needs to be done directly on the applications just to get them ready to even start. Finally, I'll point out that I said earlier that our applications can be very, very specific or very, very complex and very, very sophisticated. And so we've found that asking the question, does the application build, doesn't necessarily have a simple yes/no answer. And so we've just started to adopt this notion of feature matrices that help us understand where the code is on a more granular level. So we have lists of features or libraries or capabilities or use cases that are important to the code. We can prioritize those things and understand where the status of the various high priority and low priority use cases, features, capabilities are, and then direct efforts as appropriate. We also track any workarounds or non-issues that are applied. And this has really helped us to focus effort where it's needed and understand our priorities and where we are in the code in a way that just saying, yes, the code build, no, it doesn't build, wasn't allowing us to do. All right. That kind of finishes up my section on lessons learned and the whole modernization process. And I want to go into a little section here that is based on some slides by Adam Kunin about performance evaluation. And I talked earlier about the fact that speed up is a flawed metric. And I really do mean that. It's difficult to understand what a 10x speed up means, and really if it's even useful to say that a code is 10 times faster on Sierra than it is on some CPU platform. And so Adam especially has been leading the way in trying to develop ways to characterize the code, the behavior and the performance of code on different platforms that make sense and can allow for natural comparisons. And one of the powerful ideas that he's hit on is this notion of throughput curves that we're going to talk about for a couple of slides. Now, the idea of a throughput slide is that you plot, and here we're talking about degrees of freedom, but that's essentially a problem size metric for the code. Versus a scaled, a normalized performance metric, in this case, degrees of freedom per second. You do this for one particular problem on just a single node, and you look at how the performance of the code changes as you increase the problem size. And what we've seen over and over again is that these curves tend to have a saturation point. Exactly where that saturation point may depend on the maturity of the maturity of the code. For example, if you get rid of a bottleneck, the performance might be higher, and that saturation point can move to the left. If you expose more parallelism in your code, you can move that saturation point to the left. But understanding the shape of this throughput curve is an important aspect of performance comparisons. So again, first concept, this idea of a throughput curve. All right. Second, these throughput curves actually help us characterize machine performance and demonstrate the balance between parallelism and memory capacity. So here on this graph, I am showing throughput curves for a particular ARDRA test problem. And I'm showing this result on our CTS1, which is a CPU architecture, an x86 architecture, and also on the Sierra GPUs. And you should notice quickly two things. First of all, you notice that when you reach the saturation point, the performance is much better on GPUs. And you should also notice that plateau of saturation is much broader on the CPUs. That essentially, when you fall off this saturation point, that's where the strong scaling starts to fall off. And so strong scaling is much better on CPU platforms than GPU platforms. And of course, if you have any experience with GPUs, you probably know this, that to get good performance on GPUs, you need fairly large data sets. Now, the reason these curves are important is because when you're in this saturation regime, at least for ARDRA, we are pretty confident that the code is bandwidth bound. Off this saturation point, in this non-strong scaling regime, who really knows what the bound is? And so if you're doing a performance comparison off here to the left side of this graph, what are you really comparing? What are you really comparing? It's really murky what kind of performance analysis you're doing. So when you look at performance comparisons, it's actually, especially between architectures, it's really important to understand that you are in a well-characterized problem space. In this case, a large number of degrees of freedom. This also helps you understand, plotting these curves and looking at these kinds of curves through your optimization process helps you understand when algorithmic changes move this curve to the left or move this curve up and down. Essentially, we're saying that looking at a single problem size is not the best way to look at performance characteristics. And looking at performance without talking about problem size is also not a successful or meaningful way to talk about performance characteristics. Saying you've got an 8x speed up, well, what does that mean? Saying you've got a 0 speed up. I mean, here, again, for small problems, the GPU is still slower. So, speed up is, again, obviously here, dependent on problem size. Finally, I'll point out that the other interesting aspect of this, and this is something that's very important to Adam, is that you can kind of turn these curves on their side and look at it as a strong scaling factor instead. How many processors you're running on, and these curves tell you how much room you have to strong scale, how much headroom you have to strong scale a problem before you fall off the curve and start to lose efficiency. And here, what this curve is telling us is that CPUs have a lot more headroom, so you have a lot more room to strong scale and run efficiently if time to solution is the most important thing. This helps you understand where is an optimal way to dedicate your resources when it comes time to run the code. So I really like these analyses. I think they're important, and I think it's something that we should be thinking about more as we look at performance characterization and performance comparisons between GPU and CPU. And I will pause there for any questions.
Yes. What are, concerned at the previous slide, what are examples of degrees of freedom?
So in this case, this is a finite element code. So it's really degrees of freedom in a finite element sense. The number of quadrature points, but it could be the number of particles. It could be anything that characterizes the size of your problem that you can scale in a strong scaling sense.
Okay. Let me see here. I think we can continue, David.
Okay. So the lessons that we learned in the Sierra Center of Excellence weren't limited to just porting code. We're finding that these new platforms are opening up new opportunities for large-scale workflows. And I'm just highlighting 4 things that we've learned about workflows. First of all, optimize resources at the workflow level. This means assigning things like the most compute-intensive tasks to the GPU and allocating data-generating tasks as close as possible to the corresponding consumers. It seems obvious to do that, but actually accomplishing such an optimization can be a real challenge for the scheduler. And so we found that hierarchical schedulers like Flux to be a real benefit for these kind of thing. Second, you want to use workflow management tools. No matter how good your scheduler is, you're better able to achieve fine-grained matching of resources to tasks with software that is designed to understand and track workflow dependencies in a way that your system-wide scheduler can't. Workflow management tasks can often help with workflow checkpointing. That is actually more complicated than you might think. To checkpoint a workflow, you have to not only ensure that individual components can be restarted, but that the entire collection of restarted components form a valid and consistent member of the entire workflow ensemble. And that job is far beyond the capabilities of the individual tasks, checkpoint, and restart methods. Third, use the memory hierarchy, including NVRAM, to coordinate and share data between workflow elements. Traditionally, we've done a lot of coordination of workflows through file I/O, and we're finding that really is too slow and insufficiently scalable for the largest and most complex Sierra workflows. And one of the ways we're dealing with that in El Capitan is we've got a new piece of hardware called a Rabbit that I'll talk a little bit in the next slide. Finally, complex workflows involve large teams and rapidly changing software components. And to have any chance at reproducibility, you're going to need to employ tools designed to track those changes and provide equivalent distributions across developers, platforms, and their compilers. Say just a little bit one word about the rabbits that we're going to be bringing onto the El Capitan system. These are near node local storage solutions. I've got a kind of a conceptual diagram of how they're set up here. Each rabbit is going to have 16 SSDs and a couple of spares that form NVRAM, and also an AMD EPYC CPU that can be used to run various user tools or file systems in a container. The Rabbit nodes will be directly connected to a small collection of compute nodes. So every small family of compute nodes will have their own Rabbit node. And the Rabbit will also be connected to the high-speed interconnect. That will allow tools to communicate not only between Rabbits, but locally, but also globally. So you can use the PCIe interconnect for local compute nodes, but the high-speed interconnect to connect globally. And then, of course, you'll also be able to reach permanent luster through the high-speed interconnect. So these can be used as burst buffers. They can be used as temporary local file systems, and are exactly the kind of thing that you might want to use to accelerate the data exchange between otherwise decoupled processes in the workflow. All right. Couple of words about kind of running centers of excellence in general. We found that building up our work plans over 6-month periods was a very effective strategy. That gave us about the right granularity. I'm afraid the slide here is kind of an eye chart, but we're showing here this idea of 6-month work plans. It gave us the flexibility we needed to switch between applications and also match those work plans to which applications were available at any given time. One clearly unsuccessful thing you can do is assign vendor developers to work with a code team that has, say, a big milestone due. So, matching up the times of engagement is very important on a scheduling. We also intentionally overcommitted our plans so that we put more work than we knew we could accomplish into a single plan, so that if something fell through, if something wasn't ready, if there was say a bug in a compiler that stopped process, we had something to pivot to. Finally, effective collaboration really doesn't happen by accident. You have to schedule your activities to ensure two-way engagement. Be prepared to deviate for your plan because things will go wrong and opportunities will arise. We found that investment in collaboration and software engineering tools is really important. And of course, COVID-19 has taught us a lot more about such tools than probably most of us ever wanted to know. But getting the right tools and actually using them will pay big benefits. Early in the Sierra COE, we were pretty lax about letting our vendor partners work on their corporate systems. And access to the lab machines and repositories was cumbersome and slow for them. And so we often just exchanged tarballs. This eventually led to huge problems as it became more and more difficult to update the code that we gave them and merge their changes back to master sources. And so take my advice, if you're working with vendors, make sure they get their sources from the same repo as your developers. It's going to take some upfront work and you may have to break down some resistance, but you will be glad you went to the trouble. Document sharing is critical. Instant messaging is more useful than I'd ever imagined. But finding ways to protect NDA and export controlled information and keeping those resources accessible to all shareholders across an institution can be a pretty big challenge. It's tough, but the situation is getting better. And finally, build up multidisciplinary teams and co-locate them as much as possible. So just to kind of wrap up here, I've tried to paint, I hope, a positive picture. But the world still isn't all sunshine, lollipops, and rainbows. You are going to encounter new system pains. The MPI, the scheduler, the compilers, all of these take time to resolve, but we typically do get them right as time goes on. We constantly struggle with the tension between system stability and bleeding edge system software. We have users coming to us all the time who want to run the version of CUDA that was released yesterday, but getting that CUDA version onto our system can be potentially disruptive to system stability. And so we have to balance stability versus updates. And one of the ways that you can deal with that as a developer is think about whether you really, really need that most up-to-date thing in the latest software release, or whether you can afford to stay just a little bit behind and run with a level of system software that is more likely to be stable and installable on the HPC systems that you're using. Obviously, some apps and algorithms we still struggle with. We're still working on tools to handle all of our use cases. A lot of the proprietary vendor tools were developed for communities other than HPC and don't necessarily understand things like large MPI jobs, but the situation is getting better, and the open source tools are getting better. And finally, it's still a challenge to get various parallel models like OpenMP or CUDA or HIP, various compilers, all the various different kinds of mixtures of memory handling and compilers and programming models that you might have across various libraries. Again, the situation is getting better, but there's still speed bumps in the road. I'll just put in a plug for the Radius project at Livermore, which is an open source software stack for helping you with HPC application development. We're providing software all the way from build tools to performance tools and workflow management. I'm sure there's a website that you can Google. This is a dedicated Livermore project that is pushing out as many of the foundation concepts and open source libraries as we can to make them available for the community and help you develop parallel codes. Finally, I guess this is kind of my last slide. Migrating to heterogeneous architectures has taken us years of work, but the results are worth it. As I said up front, codes are seeing big speed ups. And we've shown that it really is possible to incrementally refactor a large production code, keeping it working and also speeding it up and getting other GPUs. We've found opportunities to reduce our technical debt if you take the time and commitment to do it. The increased performance is opening doors to new science. And hopefully, a lot of the lessons that we've learned, the ecosystem improvements that we're contributing through projects like Radius will blaze a trail for others to follow. And so hopefully it's going to be easier for you than it was for us. And I guess with any time left, we'll take questions. And there's a references slide for those of you who might be interested in some of those resources.
Thank you, David. For the participants, the slides will be available later today, perhaps, or in the next few days. Yes, David, there are some questions here. What is the lab plan for codes that, say, for algorithmic reasons, lots of branching, will not translate well to GPUs?
We continue to maintain, if you watch the news, we just announced that we are acquiring a new series of commodity technology systems, CTS2. We're not going to be only GPU systems. We're going to continue to have good CPU resources for those kinds of codes. But obviously, if you can get on a GPU, the performance advantages of doing so are really hard to argue with.
Another one here, David. How do smaller code development groups, especially at universities, get buy-in for collaboration from groups with more resources, such as the centers of excellence?
So I'm not sure which direction of buy-in you're looking for. If you're asking how does a small center get a buy-in from a large center, I'm not sure I have a good answer to that question. Ultimately the answer is offer something that's so good that everyone just needs it. If you can elaborate on that question, I'll try to answer it, but I'm not sure I have a really good answer. It's a hard problem.
Okay, so now I'd like to invite the participants to unmute themselves and ask directly questions to David. Konstantinos, I have seen here you have a longer question. Would you like to unmute yourself and ask David?
Can you hear me?
Yes.
Yeah, so the question that I had was related to, out of the El Capitan experience so far, how much of an issue did you see by the fact that both in terms of hardware, there were differing capabilities between what you had with Sierra and what you're getting now. And also HIP is still trying to catch up to CUDA in terms of overall capabilities, be it managed memory or graphs, etc. It's obviously a work in progress, but as you were moving codes, were you discovering that things that the codes were using, whether they were directly using CUDA and you were hippifying them, or even under Raja, within the workings of Raja, were having issues because of these differences? And how did you deal with that?
So the first thing that I'll say is that we've found that we have a HIP backend for Raja. We are working through some compiler issues. We've already worked through some, and the situation is rapidly improving. And we have Raja-based codes that are currently running, and some of them getting fairly decent performance measurements on MI100 hardware. Now, are we there yet? No, not by any stretch of the imagination. The MI2, the next generation of AMD processors that is going to be released hopefully very, very soon, we hope are going to be even better. And we're just going to continue that process forward.
And the lack of managed memory up until recently that HMM became available, has that been an issue? I mean,
right now we're kind of faking managed memory by using some of the zero copy features that are available on the hardware. Obviously, that does slow codes down. You can adjust for it when necessary, but most of our codes, even on Sierra, found that really the best way to get performance was just get data onto the GPU and leave it there. Mm-hmm. So we've also tended to focus on kind of kernel level performance and do the comparisons that way. That also helps us adjust for the fact that managed memory may not be quite as ready as we want it to be.
And I presume you never made heavy use, if at all, of the cache line accesses that the AC922s allowed.
Specific hardware features are always tricky to evaluate. Mm-hmm. And evaluating those at this point is clearly difficult because we're on hardware that is considerably different than what we're eventually going to have.
Okay. All right, and then just one thing that I mentioned next, the degrees of freedom versus speed in terms of degrees of freedom graphs are very informative, but I think there is very interesting arguments that can be put if you use for the vertical axis essentially time per time step or some metric of that type, because especially in that case, the disadvantage of the fact that strong scaling suffers for throughput devices shows even more. You can say that I can go 27 times faster by throwing more grid points at a problem, but then your time per time step also goes up. And especially for CFD problems, that can be an issue.
So, look, there are many ways to look at performance, and I'm not going to claim that this is the one true way of doing it. It's been very useful for us. Having that scaled thing where you reach that plateau has been very important to us, and time for time step doesn't necessarily do that. Time for time step, you're going to get into a kind of a sloped linear regime. But again, if that works for you, if that's what helps you, then by all means do it.
Thank you.
Okay, so I think we are already a couple of minutes, maybe a short question, if any, left. So David is going to go through the Q&A, and as soon as we have all the answers there, we'll send the Q&A to the participants.
Yes, because I have all of the answers. No, I'll do my best, but I'm not going to promise all of the answers.
So with that, I'd like to thank you all. And also, let me see here, I'm going to share my screen. And I'd like to thank you all for participating. Thank you very much, David. And also, I'd like to announce the next webinar in the HPC Best Practices series. It's going to be on November 10, 50 plus years in high performance computing, one woman's experience and perspectives from the presenter. The speaker will be Jean Schuller, also from Lawrence Livermore. I think she'll share very interesting stories with us. With that, thank you all for joining us today. Thank you, David. And we'll be communicating.
All right, it's been a pleasure, and I hope everyone enjoyed the talk today.
Thank you.